Hey guys, in this video we're going to be walking through the Generative Adversarial Network, or the GAN. We're going to be talking about how it works, we're going to be talking about the loss function, we're going to be talking about how to train it, and we're also going to be weighing up the pros and cons of this network architecture. Now, GANs are really cool because you can give it a training set of images. So let's say I have a training set of horses. I can give it that training set and it will learn what a horse is and it will be able to generate new instances of horses that were not in the original training set. So you can give it, images of um, images of faces, and you can train the GAN and it will be able to generate new images of faces that were not originally in the training set. So that's what makes these generative models super interesting. Now, GANs are actually one of the more basic generative models. There are more interesting and more complex models. You've probably heard of Stable Diffusion, you've probably heard of DALL-E, and these are all based on diffusion models. So in this video, we're going to be going through the GAN, and in the next video, we're going to be going through these more complex architectures. But as for now, let's just understand how GANs work and let's just see how we can build one of these. Okay, so the objective of a GAN is to generate images, and we're giving a training set of images. Now, in a GAN, we have actually two neural networks, a generator and a discriminator, and these two networks have opposing objectives. Now, the discriminator aims to become excellent at distinguishing between real and fake images. So, given a real image, it will say that this image is real. Given a fake image, it will say that this image is fake. Now, the generator wants to fool the discriminator. So, the generator wants to generate these images that will make the discriminator believe that they are real. In fact, even though they are actually generated. So that's why these two networks are actually clashing in their objectives. So I think it will make sense if we go through a diagram and see actually how this works. So what the generator does is it takes some noise, some Gaussian noise, and it converts that into a generated image. So for this whole video, we're going to be taking the example of horses. So we're going to train this GAN network to generate horses. So this generator will take this noise and it will output a image of a horse, or we hope that it will output an image of a horse. Now what we do is we take this image and we feed it into the discriminator. Now what the discriminator does is it takes in this image and it will spit out a probability. One means means that the image is real, and zero means that the image is fake. Now, in addition to supplying these generated images to the discriminator, we're also going to be supplying some training set images to the discriminator. This is so that the discriminator can actually learn what an actual image of a horse looks like. And that way it will be able to learn how to distinguish real horses from fake images of horses. So we input these training set images into the discriminator. Now, what does an ideal world look like for the discriminator, and what does an ideal world for the generator look like? If the generator were to win in this competition, what would that look like? And if the discriminator were to win in this competition, what would that look like? Let's take a look at that. So in an ideal world for the discriminator, so in like discriminator heaven or something, um, given a generated image, the discriminator would want to output 0. And given an image from the training set, the discriminator would want to output 1. That's an ideal world for the discriminator. In this world, the discriminator is able to accurately distinguish between real and generated images. Okay, how about an ideal world for a generator? For the generator, the ideal world is that when we give the generated image to the discriminator, it outputs 1. So the discriminator believes that this image is real, even though it's actually generated. So you can see how these two objectives are actually opposing. Specifically, this objective and this objective. They're literally direct opposites. So you can see how these two networks are competing, and in the end, we actually want the generator to win. So we want the generator to be able to fool the discriminator. That's the objective. But to actually get there, we need to have this discriminator and we need to have these opposing objectives so that the generator can actually learn how to generate new images. Because this is kind of like the feedback for the generator. So if the discriminator is able to tell that the generated image is fake, then that's feedback for the generator to improve. But if the discriminator isn't able to distinguish between real and generated images, then that's feedback to the generator that, okay, you've done a good job. So we need this discriminator to give feedback to the generator. Okay, now that we've got that, let's actually get into a little bit of some math just to get the loss function down. So, okay, let's actually not. Okay, let's delete this for a while. Okay, so let's just get some notation down. So X is the training set image, and I think it would be useful to have this image as well. So let's just copy this and put it here. You come over here. Okay. Right. So X is a image from the training set. So we can see that X is an image from the training set. Z is Gaussian noise. So just some noise, which the generator then uses to generate the image G of Z. So that's G of Z. G of Z is just the generated image. Now we pass this image, we pass this generated image or this training set image into the discriminator. And for each of those cases, we get two probabilities. So D of X is the probability that a training set image is real, and D of G of Z is equal to the probability that a generated image is real. So remember, the discriminator is just a binary image classifier which tells us whether the input image is real or whether the input image is from the training set distribution. That's a more specific term. So if D of G of Z is the probability that a generated image is real, then 1 minus this is the probability that a generated image is fake. Okay, now that we have those terms down, let's go through the loss function formulation. So I know this kind of looks complex and a little bit hard to read, but I think by the end of this, you'll see that this is actually very intuitive, and the components of this loss function actually make a lot of sense. So let's get right into it. Here we have an arg min max, so this is an optimization problem, and we have this entire expression here. So the generator, or G, is trying to minimize this expression, while the discriminator is trying to maximize this expression. So let's go through these dot points one by one so we can understand what this loss function actually means. Okay, the generator wants to minimize the probability that fake images are deemed fake by the discriminator. So that's this component right here. This log of 1 minus d of g of z is the probability that fake images are deemed fake. And the generator wants to minimize that. So the generator wants to minimize this value. And if you need to take a second to pause and actually, think through how that makes sense, I would highly recommend doing that. That's the best way to understand this. Okay. Next, the discriminator wants to maximize the probability that real images are deemed real. So that's this log of d of x right here. And log is just a function that takes a number and makes it really small. So it's just for making the trading more stable. So don't worry about the log. All right. Log of d of x is the probability that real images are deemed real, and the discriminator wants to maximize that. And the discriminator also wants to maximize the probability that fake images are deemed fake. So remember, this expression right here is the probability that fake is the log probability that fake images are deemed fake. And the discriminator wants to maximize that. It wants to maximize its accuracy in deeming whether real images are real or fake images are fake. But the generator wants to minimize the probability that fake images are deemed fake. Okay, so I hope that made sense. And one more thing that you should take note is that even though it is shown here that the generator minimizes this whole expression, the generator really only cares about this expression right here, the second expression, because the generator has no effect on what happens to the training set images. Remember, the generator doesn't actually look at the training set images at all. That's one of the really cool things about this. The generator doesn't even take a look at the um, training set images at all. It's solely relying on the feedback from the discriminator to update itself and to indirectly learn what a horse looks like. Okay, so generator is just trying to minimize this expression right here, and the discriminator is maximizing this whole expression. I hope that made sense. If it didn't make sense, just go back, rewatch it, and I hope you'll understand it. Okay. So now that we have the loss function, we can get into how to train this system, this GAN system. Okay, so to train this system, what we do is we train the generator on one example, train the discriminator once, and we repeat that process over and over. Okay, so we start with some noise, input it into the generator, generate the image, feed that into the discriminator, and get the probability that that fake image is real. So let me just make it simpler. Probability that the fake image is real. So the discriminator wants to minimize this. So the discriminator wants to minimize the probability that the fake image is real, is deemed real. That makes a bit more sense. Probability that the fake image is deemed real. And yeah. So in the loss formulation, we had a min-max formulation, but to actually implement it, we're just using minimization. So that's how neural networks learn, through minimization. We rarely use maximization. So we just need to reframe this to so that we can implement a minimization. So the discriminator wants to minimize this, or the log of this, and the generator, so what we do is take 1 minus this. So if this is the probability that the fake image is deemed real, 1 minus this is the probability that the fake image is deemed fake, which the generator doesn't want. So we want to minimize that. Okay, so this is for generated images, but the discriminator is also going to be seeing the training set images. So we input a training set image into the discriminator, and it outputs the probability that the real image is deemed real. And the discriminator wants to, um, so the discriminator wants to maximize this. But to put it in a way that neural networks can learn, we do 1 minus this, and then we minimize that. So instead of maximizing this, we minimize 1 minus that. I know it's a little bit strange, but that's how neural networks learn. Okay, so that's training. So once this is done, once so we input a generated image, then we input a training set image, and then we keep repeating that over and over. By the end, we'll get a generator that is really good at generating these images of horses, and the discriminator is actually not able to distinguish between the generated images and real images. That's how we know that training is done. Okay, so after training, now we can use our generator to generate new images. So the discriminator job is actually done. We don't need it anymore. So we essentially throw it away. And now we can use the generator to generate new horse images. So we input some Gaussian noise, some random noise, into the generator, and we get this horse image. If we input a different Gaussian noise into the generator, we get this horse image. And if we input a different Gaussian noise, we get this image. So you can see that the Gaussian noise is actually the reason that the generator is able to generate new instances. Because by changing this Gaussian noise, by making a different Gaussian noise, we can get a different generated horse. And this is actually really, really marvelous, really fascinating, how the generator is able to take noise and transform it into an image of a horse, or into any image. Okay, so that's how the GAN works essentially. I think. Okay, yeah. Let's just quickly go over some pros and cons of the GAN architecture. So the pros of the GAN architecture is that it can generate high quality images if it's trained properly, and this is all unsupervised, so we don't need any labels at all. We just need a training set of images. Okay, how about the disadvantages? Well, GANs are very hard to train because we're training two networks at the same time. And if we don't get the training pace right, if one network is learning at a slightly faster pace than the other, then we won't get really good results. So we really need to make sure that the networks are training at the same pace. Another really challenging and significant problem is called mode collapse. So mode collapse is when the generator produces the same image every time, and it's still able to fool the discriminator. So if we had a generator that just outputted this image of a horse every time, so regardless of the noise that's coming in, it just generates this image all the time. This is actually enough to fool the discriminator because this is a believable image of a horse, and when we give it to the discriminator thinks this is real. So the generator actually learns a shortcut. It learns that it doesn't actually need to output a different image time every time. It just outputs this single image, and that fools the discriminator, and its job is done. So that's one of the problems that can happen with GANs, and it's called mode collapse. But if you are able to, train the neural networks correctly, train these at the same pace, then you still actually get really good results. All right, so that's the pros and cons. And that is basically the GAN architecture finished. So in this video, you learned about the GAN architecture, you learned about the generator and the discriminator, you learned about how they are competing together and that they have opposing objectives. You learned how they are trained, you learned about the loss function, and you learned about some advantages of GANs and some disadvantages of GANs. The next thing for you to do, which I would highly recommend, is go to this tutorial on TensorFlow. And this tutorial actually shows you how to implement a GAN from scratch using TensorFlow. So in this tutorial, I believe you implement a GAN which generates MNIST digits. Yeah. So in this tutorial, you use TensorFlow to build a GAN that allows you to generate new instances of MNIST digits, which I think is really good. And then you can, once you finish this, you can try out different collections of images. You can try out horses, try out faces, do whatever you want. But I would highly recommend following this tutorial, getting into the code, and actually figuring out how this GAN works, because the code is the truth. The code is the source of truth. So once you get into the code, you'll be able to, really understand how this GAN works. All right. That's pretty much it for this tutorial, for this walkthrough of a GAN. I'm going to be putting this link in the description box below. I'll also put the link for this Figma file, so if you want to go through these diagrams and just review them, you can do that. But in the next video, we're going to be talking about the pix-to-pix architecture, which is used for image translation. Image translation is basically taking an image from one domain and transforming it into another. So we can take a horse and transform it into a zebra. That's the next video. Yeah, that's pretty much it for this video. If you enjoyed it, if you want to see more videos and you want to stay updated about when the next video comes out, make sure you subscribe. And yeah, that's it for this video. Have a wonderful day. Thanks.